Okay, so one other application of this breadth first search algorithm is to find the um, path, shortest path and the length between, or the shortest path from some vertex to the other rest of the vertices in the graph. So using breadth first search, we saw that we can find the level numbers of the vertices on the shortest path from a starting vertex. So for example, on this graph, if I start from A, the numbers I have written here indicate the level numbers, which is also the distance or the number of edges on the shortest path from starting from A to these vertices. So from A you can go to B to a path of length 1, from A you can go to C to a path of length 2, from A you can go to F, you can to a path of length 3, and so on. Now, so what we can do is we can build what is called a distance matrix that represent the shortest path length from each vertex to the other vertices. So here you have a graph of 8 vertices, and so you can have an 8 by 8 matrix, and we have from vertex 1 to the rest of the vertices. From 1 to 2 you have an edge, so that's the path length 1, 1 to 3, the shortest path is of length 2, 1 to 4, the shortest path, like you can go from 1 to 6, 6 to 7, and 7 to 4 of length 3. 1 to 5 will be length 1, 1 to 6 will be length 1, 1 to 7 is length 2, 1 to 8 is length 3, 1, 6, 7, 8. So if you run breadth first search starting from 1, you can get all these values for path length. So similarly, if you run breadth first search from the other vertices, you will be able to find the path length from that vertex to the rest of the vertices. So that gives you a distance matrix. So once you get the distance matrix, you can come up with what is called the eccentricity of the vertices. So eccentricity is a node level metric. So for each vertex you can compute what's called the eccentricity of the vertex. And the eccentricity of the vertex is the maximum of the shortest path length from that vertex to the rest of the vertices. So in this row for vertex 1, the maximum value is 3, and that is eccentricity of vertex 1. In this row again, the maximum value is 3, that's the eccentricity of vertex 2. So likewise, now if you look at vertex 6, the maximum value of the shortest path length is 2, and that's the eccentricity of vertex 6. Similarly here, the eccentricity of vertex 7 is 2. So once you find the eccentricity of the vertices, you can come up with the diameter and radius of the graph. So diameter, radius, and center are at the graph level. Okay, so the diameter of a graph is the maximum of the eccentricity values. So that is 3. And the radius of a graph is the minimum of the eccentricity values, it is 2. Now the diameter is a very important metric because it gives you an idea of what is the maximum length of the path, or what's the maximum path length for a shortest path between any two vertices. Okay, so it's very important that we keep the diameter at an optimum level. We cannot keep it to be 1. If you have to keep it to be 1, then any vertex has to be connected to any other vertex, so that's not kind of feasible. So for example, in a communication network, okay, so if you want, say these are the different routers or the computers. So if you want to minimize the distance between any two communicating devices, then you want to minimize the diameter, but you cannot just be linking every computer to every other computer. That's not possible. On the other hand, you should not also have them like a chain. That's the maximum diameter. Okay, so diameter should be as low as possible given all the cost things that are involved. Okay. Then the radius represents the minimum of the eccentricity values, and the vertices whose eccentricity is equal to the radius are said to be part of what is called the center of a graph. So here 6 and 7 are the two vertices whose eccentricity is equal to the radius. So we say 6 and 7 are forming what is called the center of the graph. So it's like the core or the backbone of the graph. and every other vertex is considered to be in the periphery attached to some vertex in the center. So 1, 2 and 5 are kind of attached to 6, 3, 4 and 8 are attached to 7. So these other vertices are considered to be like peripheral vertices. Now you can also come up with what is called the average path length, which is this Wiener index divided by the number of pairs of vertices we can consider. Okay. So the Wiener index is simply the sum of all the non-zero distance values you have in the distance matrix. So how can we compute that easily? Just for each row, first come up with a sum. Okay, so these are the 1 plus 2 plus 3 plus 1 plus 1 plus 2 plus 3 is 13. So like that, come up with a sum of the shortest path length values from a vertex to the rest of the vertices, and then add all these numbers, 13 plus 13 plus 13 plus 16 and so on, we'll get 106. And how we got this 106, in each row we considered all the non-zero distance values. So there are 8 vertices, so you're going to consider 7 non-zero, 8 minus 1 non-zero distance values. So the distance from a vertex to itself is 0. So that is why if you have n vertices in general in the graph, you're going to have n minus 1 non-zero distance values for each row. And there are n such vertices, 8 vertices in this case, so it's 8 times 7 in the denominator. So that gives you the average path length. So I have another graph here. So this is a kind of another way to represent the distance matrix. I would prefer this one because we'll use this for other modules too, but sometimes you can write also like a vector. So the distance vector starting from for each vertex. So vertex 1, so these are the distances in the increasing order. So to vertices 2 and 3 the distance is 1. Then to 4, 5 and 6 the distance is 2 for vertex 1. For vertex 2 there are 3 shortest path length of 1, which is to 1, 4 and 6, and to 3 and 5 the shortest path is of length 2. So that is how you have to interpret this vector. So it's written in the increasing order of the shortest path length values. And then the eccentricity as usual is the maximum of this shortest path length values for each vertex. So the maximum of these entries is 2, maximum of this is 2, again this now maximum is 3, and so on. Now the diameter is the maximum of the eccentricity values of the vertices, which is 3 in this case, and radius is 2. And the center of the graph is those vertices whose eccentricity is equal to the radius, which is in this case 1, 2, 5 and 6. And Wiener index is the sum of all these non-zero distance values, that comes out to be 48. And you have again here 6 vertices, and each vertices you have 5 vertices in the distance vector, so it is 6 times 5 in the denominator. Okay, so that's how we get the average path length. Now one important thing to remember about or to know about the average path length is for the real world networks that are out there, what is the average path length we see as a function of the number of nodes in the graph. Okay, so for example, in Facebook you have 721 million users, but you see the average path length between any two users is 4.74. So that's indicating that you could reach from one user to another user through some 4 or 5 intermediate users. Okay, so even though there are a lot of users out there, it's still looking like a small world. You can get to know or reach one user to another user through 4 or 5 intermediate users. Okay, similarly, the World Wide Web has 50 million pages, and the average path length between 2 pages is 3.1. Now there's a link between 2 web pages if one page is having a link or citing another page. Okay. Now these people also observed that the diameter, okay, could be reasonably larger than the average path length, and okay, so for these for co-author networks, they found in these different areas in math and other areas, they found the average path length is 7.6, whereas the diameter is 27, and 5.9 and 20, and so on. So in our case, you got like 1.6 and 3, 1.89 and 3 is not reasonably different, but here you see it's 7.6 and 27, 5.9 and 20, 9.5 and 29. So for real world networks, you could see the diameter to be sufficiently larger compared to the average path length. Okay. Now, again, the diameter is like a worst case path length between any two nodes, but on average, okay, what's the path length that is captured by the average path length? Okay. Now, so we can say a real world network is exhibiting a small world property if for a network of n vertices, the average path length is proportional to log n. So this is natural logarithm of n, so log to the base e of n. So if n is 100, log n, log to the n to the base e is 4.61. So if for some real world network, okay, if you find its average path length is kind of close to log n, not like very it's all the same as log n that you get. If it is somewhere around log n, then we can say that network is exhibiting small world property. So you see, as you increase the number of nodes in the network, okay, 10,000, the log n function is a slow growing function. It's kind of almost just doubling. And then the n is like 10 million, log n is still like increasing very slow, 16. Okay, now for so that is, so we say the network is exhibiting a small world property if the average path length is kind of close to log n. Now, if you can even, there's some other networks also exhibiting what is called ultra small world property. Here, the average path length is proportional or close to log n divided by log of log n. So it's like if n is 100, log n is 4.61. Log n divided by log of log n is 4.61 divided by log of 4.61, and that comes out to be say 3.02. For n is 10,000, log n is 9.21 divided by log of 9.1 is like 4.15. And for 10 million, log n is 16.12, log of 16.12 in the denominator. So log 16.12 divided by log of 16.12 is like 5.79. So this ratio is even smaller than log n. So if a network is exhibiting a path length that is proportional to log n divided by log of log n, then you can say the network is exhibiting ultra small world property. Okay. So later we'll see more detail about random networks and scale-free networks. Okay. So we'll observe the random networks it will exhibit small world property, where scale-free networks, most of the real world networks of scale-free in nature, exhibit ultra small world property. Now for the graph that is assigned to you here, we can decide whether it is exhibiting small world or ultra small world property or neither of them. So what you can do is, once you find the average path length and you see there are 8 vertices, so take logarithm of 8, it's like 2.079, and we got 1.89 as average path length. Let's go ahead and find log of, so log n divided by log of log n. So divided by, you can type 2.079 and take the logarithm of that. You will get, let me see, log of, okay, so log of 8 is this, divided by okay, you see here, when you take the logarithm of 2.079, which is log of 8, you get a fraction, some value even less than 1, right? So that's why you get log of 8 divided by log of log 8 is to be actually greater than log 8, 2.84 greater than 2.079. So if the numbers are very small, so the number of nodes is very small, right? We will just focus on the small world property, not on the ultra small world property. If the numbers are very large, okay, or reasonably large, let's say 100, so as long as the denominator log n is greater than or equal to 1, this value, this ratio will be less than log n. If the denominator log n is less than 1, it will be, this ratio will be greater than log n. Then it doesn't make sense to talk about ultra small world property. So for the small graph that we have here, and as well as also in exam 1, we'll just test for small world property, not for ultra small world property. So here also we get like there are 8 vertices, so 6 vertices. So let us check here, 6 vertices, log n, log 6 is 1.79, so close to 1.6. So we can say it is small world property. But if you try to find divided by log 6, it's going to be even greater than 1.79 because it's 0.58, it's a fraction in the denominator. So it's going to become greater than log 6. Okay. So let us just test for small world property for very small graph like this. So with that we stop this video.